In Chapter 5, we focus on stereoisomerism. It's a different way that we can look at carbon-based compounds. In order to get an understanding of this situation, I want you to take a piece of paper and write out the molecular equation for each of these compounds that are shown on the screen here. Are these the same molecule? Are these not? What do you think? So take a moment, pause this, and write down these two compounds and tell me if you think they're different. So once you've drawn these out, you might look at them and tell me, yeah, these aren't really different. And I'm going to tell you they actually are, and we're going to talk about in this lecture how they are and why they are and how you can identify if something is a stereoisomer like these are. One of the ways that we actually know that these different types of compounds are different is that they respond to light in a different way. They actually have optical activity. So here's an experiment that's looking at a polarimeter, and basically it's a pretty simple little device where you have a tube and you have either a solution or a solid crystal structure of something, and you'd put it in this little sample tube and you put light through it. And if you put light through it, that is actually if you have some type of polarizer or film that will only let certain light in a certain orientation go through, and you put it through that sample here, you'll actually notice that the light will get rotated out of this solution after it hits it. That interaction with the molecule will rotate it if it is one of the types of compounds versus the other. So we have these different ways that we can identify this. If we have a D, it means dextra rotary, which means right hand. If it's an L, it's lever rotatory, and it is the left-handed turning of that light that's actually happened. So these are different terms that we're going to determine. There is another way that we can name this. We're going to go through a naming system for these, and it will actually use R versus S, and that's a different way. So this is nothing, that's the naming system. That doesn't necessarily mean that it's going to turn light right or left-handed way. So these were identified and determined at different times and given different names, and we'll talk about both of these systems. Certain biological compounds that have specific rotation, and some that you may recognize for sure, are sucrose. We have different cholesterol-based compounds like epinephrine and testosterone, progesterone, for example. Glutamate is an amino acid that has a specific rotation. So these are biologically relevant compounds that have rotation, and that means that they have this right or left-handed orientation. And we're not going to get into this too much. I do want to introduce it to you though. This alpha in brackets is talking about the amount of rotation. So the 99 plus 99 plus 55 minus 136, that's the amount that the light is going to get rotated in that certain compound. And this is based off of temperature and the wavelength of light that we're putting through. That'll all change based off of those criteria. And here we have is equivalent to that change in the rotation over the path length times the concentration of the compound that we have in solution. So you can use this to kind of solve different parts of how much is it rotating. You can figure out the concentration. You can do all sorts of different things with this type of technique. This is just an example of if we're looking at glucose, for example, D-glucose, we're going to be able to rotate. That's going to rotate if we have 25 degrees Celsius, and we're talking about the D in this instance is the line of sodium spectrum, so it's 589.3 nanometers. If we're using those as our constants, temperature and light source, then we're going to rotate that 52.7 degrees. And so this is just some of the information about D-glucose. And you can see glucose here, we have D-glucose is the glucose that we can eat and consume and recognize. L-glucose is a different compound, and it's basically just this last carbon where that hydroxide group is, if it's on the left or the right. And we'll talk more about how we identify these different stereoisomers as well. But I just wanted to introduce this idea to you. I'm not going to get into this too much, but the book does walk through this idea a little bit, and I do want to introduce it to you. So sometimes when chemical reactions are happening, especially in organic chemistry, we will generate one type of enantiomer versus another. And this process can generate, again, if we're looking at 20% S versus 80% R, these will cancel each other out in equal amounts. So that's what we're kind of doing here. So if we have 20% S, that means that 20% of the R signal is going to be canceled out. So you'll get a signal out that's overall, since these cancel out, we'll get 60% excess. And it will look like we have a 60% rotation based off of the kind of essentially eliminating the other 20%. And this is the equation that is typically used, the enantiomeric excess, EE. If you have the different specific rotation of the mixture versus the pure enantiomer multiplied by 100, you can get that percentage. And that is just kind of telling us basically what, looking through these things. And we're not gonna go into detail on this. I don't think it's worth spending too much time on this. I just wanted to introduce this concept to you. This is something, if you were to take advanced organic chemistry, we might spend a little more time on. I will go through just one example problem just in case you were interested in looking at this. If we're looking at cholesterol, what is the enantiomeric excess for this if the alpha of the mixture was found to be 6.3? So if it's 6.3, that means that we would have to divide that by 31.5 times 100. So that is the mixture, that's the 6.3 divided by the pure enantiomer. And the pure enantiomer we can see is 31.5 multiplied by 100, and then I would get 20%. So that is the enantiomeric excess. That's the EE, for example. And that means that that's this value. So if we take 100 minus 20, which is the enantiomeric excess, that gives us 80% racemic mixture. So that is this part over here. And then if I divide that by 2, that's actually going to give me 40% of the enantiomer, and 60% is the cholesterol. DNA is another type of chiral compound. It means that we have these right or left-handed versions of this, and they're mirror images. So if we look at this little example of a kind of corkscrew, this is the similar type of way that DNA is set up. So if you were to look at this, which would you think is DNA that's shown here on the right, a left or right-handed screw? And the way that we can kind of figure this out is if we kind of put our hands on the blade and try to go up or down. The way that if we use our right or left hand, if you use your left hand on the left screw, you should be able to kind of go down on the sides of the edge, kind of the blade part, and your thumb will point down. That means it's left-handed. And if you will go with your right hand around on the blade part, your thumb will go up. That is right-handed. So you can't necessarily do that same thing. You'll be kind of going the opposite way if you use the wrong hand on these. So if you were to kind of grab and try to put your hand on the blade, which would be this part right here, on a DNA helix, you're going to be using your right hand and it's going to give you a thumbs up. So this DNA helix is actually right-handed. So these are all biological compounds, and they come up to be these enantiomers, and they come up to be this pure compound that gives us specific rotation. If we were to synthesize this in an organic chemistry lab, it's possible that we would generate racemic mixture where there would be equal amounts of these two different types of enantiomers. Why would biological compounds exist as pure stereoisomers where if we synthesize this, it might be a mixture? So take a moment and write that down. We'll come back to this in the class. So keep track of that, and we'll talk about this when we meet up again. So we haven't talked about the reason that these are all left or right-handed in biological systems, but what is really important is that they actually are right or left-handed, and there are big differences that would happen if we ended up switching that around. So there are the biological properties that we're looking at when we look at an example here is L-DOPA. So L-DOPA is a precursor to dopamine, and it's used as a Parkinson's drug. D-DOPA is actually biologically inactive. So if we gave D-DOPA, we give the wrong form of dopamine as a drug, it wouldn't do anything. It wouldn't work. So we need to give the correct handed side version of that. Some drugs, if we have the left or right-handed version, are deadly or poisons instead of drugs or things that are going to help. So there can be very vastly different functions of these depending on if they're right or left-handed. Just this little change in the orientation of these 4 different groups coming off of that central carbon. D-DOPA, just so you know, is actually a precursor to dopamine. It's given because it's more because it can pass the blood-brain barrier where dopamine can't. So you give it the precursor so we can get to where it needs to go. So we're going to cover a few more vocab words, and you know, organic chemistry, there's a lot of vocabulary. There really is. So we need to know and understand what these words mean so that we can have conversations about them, and so that you can take your quizzes and exams and understand what I am asking. So chirality is one of these terms that we need to know. And objects can be either chiral or achiral. In other words, you can have the top, this is an achiral compound because that chair the mirror image is superimposable, meaning that I could take this chair and I could kind of put it over the top of this other chair and it is superimposable. This chair is chiral, which means it's not superimposable because this is a right-handed chair where someone who is right-handed would be able to write notes in it easily. This is a left-handed chair where someone with a left hand might be able to write notes more easily, for example. And if we were to try to superimpose this, you would notice you wouldn't be able to kind of sit in the chair because there wouldn't be an open side to kind of enter in and sit down through. So these are chiral, and the top chair these are achiral because of that superimposability. Achiral things will often have a plane of symmetry. So this cup, for example, has a plane of symmetry down the middle. However, your hand doesn't have a plane of symmetry. If I cut this down through the middle finger, or I have a thumb and a pinky, those are not the same. So that actually makes a difference where we do that. If we go back a slide, if I cut this chair down the middle, the right and the left side are not the same. However, if I cut this chair down the middle, the right and left side are the same thing. Now, instead of cups and hands and all that stuff, let's get into molecules and start looking at these and trying to identify chiral versus achiral. Here we have mirror images, and you'll notice that we can align both of these. And also notice there are only 3 different types of atoms. We have hydrogen, we have the bromine and the chlorine. So there are 2 hydrogens here, and we can rotate these around so that we can organize them and align them. So this top element is achiral. There is a line of symmetry down the center. We can kind of cut it between those 2 protons down the center, and we can superimpose them. Here we have CHBr, ClF. We have hydrogen, chlorine, bromine, and a fluorine. And now when we try to superimpose them, you'll notice we can't do it. They don't align because of that difference in the chirality. The mirror images are not superimposable, and so this compound down here these are chiral compounds. So does 2-chloropropane have a plane of symmetry? Pause this, look at it, and bring your answer to class when we meet next time. What about 2-chlorobutane? Pause, answer your question, write your answer down, bring this to class. Chiral centers are these compounds that have these mirror images that are non-superimposable, and it also requires that the compound, the center, or the carbon here, has 4 different unique different things attached to it. So here we have a methyl group, here we have a carboxylic acid group, here we have a hydrogen and an alcohol. So there are 4 different things that are attached. Their mirror image selves are non-superimposable, and that means they're enantiomers. And so these are called chiral centers. So there's another vocab word for you. The way that we determine if something is chiral or not is by identifying centers where there are 4 different unique things attached. So here this is one carbon that has 4 things attached, but 2 of these things are the same, actually on both sides. So this is achiral. Here we have 2 of the same things attached to that center carbon. So this is also achiral. Here we have 4 different unique things. This would be chiral. Here's another carbon center. All of these carbons here, these have 2 or 3 things that are the same, so those could not be. We have a methyl group versus an ethyl group. Those are different things, a hydrogen and a bromine. So this is a chiral center. That center right there. Here's another carbon center. We have a methyl group and a methyl group, so those match, and that's going to be achiral. So that is not a chiral center. Here on this bottom one right here, we have 1, 2, 3, 4 carbons versus 1, 2, 3, 4, 5. Those are different. So those are different groups from the left to the right. And then we have a hydrogen and a bromine. So this is also going to be chiral. And here we can count 1, 2, 3, 4, 5, 6. I don't actually have to count the other side. We have a double bond. That makes it different. Hydrogen and a bromine. This is also chiral. So we'll practice. I have a different worksheet. We'll go through looking at some more of these to practice this a little bit more. But this is just an example of how to identify chiral centers. Now here's a big trick. One element that we are looking at most commonly in this class is carbon. And a lot of times carbon will be attached to 4 different things. So we just need to figure out if it is attached to 4 different things. If it's attached to 2 or 3 or 4 hydrogens, it's not a chiral center. Oxygen, remember, has 2 lone pairs. So that's typically not going to be a chiral center. Nitrogen has a lone pair, and typically it's attached to 3 things. If it could attach to a 4th thing, it is possible nitrogen could be a chiral center, but it's not very often. So mostly we're looking at carbon. So look for the carbon and identify if we have more than, or if we have 4 different things attached to it, then that might be a chiral center. So the next thing we're going to do is we're going to talk about R and S nomenclature. So this is a kind of similar idea as the D and L nomenclature that talks about the rotation of light, but that's a physical property. That's actually something that light will change based on how it's going through. This is a naming process. So we don't necessarily know how light is going to be influenced by this molecule or compound, but we're just using the system to name it in order for understanding how to draw it out properly. So with this name, I should be able to draw something out, and I should be able to draw something out and name it. So this process that we're going to look at is to assign priority is an important part of this. We have to be able to prioritize these different groups that are attached to our chiral center. So that's going to be part of this process, is prioritization. And we'll talk about priority rules. So what we're going to essentially do is we're going to take the low priority compound and always get it into the back of the field of what we're looking at. And then we're looking at this is, for example, A is the high priority. This is the second highest priority is B, and C is the third highest priority. And then you can, if you look from A to B to C, that's going in a right-handed configuration. So we're going clockwise, so that's right. And we're going to show you how we can kind of do this and how we can translate this other ways of looking at this. But the first step to be able to do any of this is to identify the priority. How do we name the first, second, third, and fourth place priorities here? So priority rule number one, the higher the atomic number, the higher the priority. So carbon has a higher atomic number than hydrogen, so it has higher priority. Oxygen has a higher atomic mass or number than carbon, so it has a higher priority. If you have to do the next atom in the chain, that will also have a higher atomic number. So if we have a methyl group or a C group, then we might have to go down the chain further. So here we have carbon attached to 3 hydrogens. This carbon is attached to 2 hydrogens and 1 carbon. So as we go down the chain, this carbon has a higher priority than one of these hydrogens. So this compound has a higher priority. If we have a carbon that's double or triple bonded, it's as if it is bonded to 3 other carbons. So here, this carbon, it's represented as we have a carbon, carbon, and carbon. So this carbon, it's like it's attached to 3 carbons. So that will help you determine the priority. If we have double bonded anything, oxygen, carbon, nitrogen, that carbon, it's attached to 1 hydrogen and 2 oxygens, as it's shown, 1 carbon and 2 oxygens. So that's essentially how we determine priority for these different compounds. So you just have to, if we get long chains, you just have to keep going down the chain until something is different. One thing that I should point out when we are looking at these diagrams is that these lines that are drawn, just kind of flat, straight lines, those are meant to be drawn and kind of thought of as being drawn in the plane of the screen. But the dashed lines are, you're kind of imagining that that's going back into the screen, and the wedge here is coming out at you out of the screen. So that's kind of why we can look at A, B, and C. We can do this right-handed or clockwise turn versus this compound where it's A and B and C. You can see the C is going into the screen versus here it's a B. So we've rotated where those are. And this is now a left-handed turn or a counterclockwise spin. So that's an S molecule. So we're going to have to first determine the priority and then be able to determine if we're going right-handed or left-handed in counterclockwise or clockwise in terms of spinning these, how we would go from 1, 2 to 3 priority. So I want you to assign priority for the compounds above, and some of these get a little more difficult. So just try to practice some of these in terms of how we assign priority. And looking at this top ring here, we generally know that so the hydrogen is going to be the low priority, and it's going to, because it's the lowest atomic mass thing that is attached. Here we have a methyl group, and a methyl group. So the star is indicating that's the chiral center. So we have 3 methyl groups. So right now we have the same priority. But after the next step, we know that this carbon on top is attached to 3 hydrogens. So that has to be the second lowest priority. Now we'll keep kind of going out on these branches, and I hit another carbon, and I hit another carbon. And now there's a difference that the carbon on the right side is attached to 2 other carbons, and the carbon on the left side is only attached to 1 other carbon, and then 2 hydrogen atoms. So we know that this is, on the left, that is the next lowest priority. So that is priority number 2. And then, sorry, this should be up here 2. And then going down the right side, that will be the high priority here. So we're going to talk about how we can determine if this is right or left later. But now let's just assign priorities here. Here we have another chiral center. And I'm going to kind of walk out on all of these different chains. And we have carbons on each of those at that point. I know that this methyl group on the top is going to be the low priority because that's attached to 3 hydrogens, and the other groups are attached to multiple bonds. The carbon right here is attached to another carbon. And the carbon on top is attached to 2 carbons. This carbon's technically attached to 3. So we know then that this is 3, 2, and this is the 1 priority because of those double bonded rules I talked about on the last slide. Here's another chiral carbon, and I'll walk out 1 unit to each of my next attached molecules. I have a carbon, a carbon, a carbon, and a carbon. And this is, again, on the right side, that's the low priority because it is attached to methyl groups after that. The carbon that's attached now singly to another carbon, that's going to be the 3rd priority. And then my 2nd priority is actually going to be this carbon, because we have a carbon versus an oxygen. Oxygen is a higher molecular weight. So this is actually going to be my number 1 priority group. Finally, we go here. This is a chiral center. We have a hydrogen, we have a deuterium, a methyl, and an oxygen. Hydrogen is a lower molecular weight, so that's 4. Deuterium has 2 neutrons in its nucleus, so that is actually heavier than a hydrogen, so that is 3. Oxygen is heavier than carbon, so the carbon is 2, and then the first priority is 1. So you have to take into consideration if we have heavy isotopes as well. Those get a higher priority than their lower molecular weight isotope counterparts. So now we're going to talk about, so we have determined some priorities with different compounds. The next step is to determine if they're R or S in terms of how we would determine their naming. So in this example, I am going to just show you that we have these groups, and they can be anything, right? A, B, C, and D. They're just 4 different things. And I've ranked these over here in green. So we're going to say unit D is 1, first rank, A is a 2nd rank, C is 3rd rank, and B is the 4th ranked group. So here is our chiral center in the middle. And some of the rules that we need to do is we need to ignore the low priority. So the low priority in this instance is B. And we're going to put it in the back through this dashed line. So this is in the back of our molecule. And then we're going to trace from 1 to 2 to 3, and we're ignoring whatever is in the back of the molecule. So I'm going to go from high priority 1 to 2 to 3. I'm skipping and just ignoring and going right over 4. And so we know that this is shown as an R enantiomer because we trace from 1 to 2 to 3. So let's look at a few examples like that. Here's a simple example where we have iodine, bromine, hydrogen, and a carbon. Hydrogen is the 4th priority because it is the lowest molecular weight group on here. We will then, it's also, by the way, helpful to have a periodic table handy so that you're able to identify what the high and low molecular weight things are. If we look at the periodic table, the methyl group, the carbon, is actually the next smallest. Bromine is the medium smallest, and then iodine is the largest thing, so the highest atomic weight. So we go 1, 2, 3, and 4. We're going to ignore what's in the back. So 1, 2, 3, that's going to be right hand. So again, this has to go into the back. So we're lucky that managed to be in the back when we drew that out. Again, this hydrogen's in the back, so it's a 4. And we can renumber all of these and identify this is 2 and this is a 1. Now you'll notice we just switched these 2 groups out. I'm going to just highlight that with different colors. So the 1 and the 2, those are swapped, 1 and 2. And that's going to change. Now we go from 1 to 2 to 3. Now this is an S. So it's the opposite direction. We went from a clockwise to counterclockwise. So that's the difference between an R and an S. And all we have to do is swap 2 of these groups, and then we actually change that from an R to an S. So it's as simple as doing that. That's going to be an important idea moving forward when we have things that maybe are not set up as easily to name them. Here are some examples of longer chained groups. We have a methyl group here, and that's going to be the low priority. It's a number 4 because we have 1 carbon attached to 3 hydrogens. And we have this carbon attached to an oxygen versus a carbon attached to a methyl group. So carbon and methyl group, that is going to be the next lowest priority because oxygen is larger and has more mass molecule, right, than carbon. So then that is 3. This is going to be 2, and bromine is the largest atomic mass component on this chiral center. So then I'm going to trace from 1 to 2. I'm ignoring 4. I'm going to 3 because 4 is in the back, and this is going to be an S orientation. All right, so what happens now when we change this up a little bit and when the low priority is in the front? So here we can do, this is the low priority, and we just did this one, so we know that this is 3 and 2 and 1. This group it has on a dash, right? So that means this is actually coming out at you. We can't get the correct answer if we do a trace right now, because this only works if this 4th group is in the back. So you have 2 options. You can redraw this, and that would be basically, I can kind of pretend in my mind that I'm kind of spinning this group around. I'm going to take this bromine and put it where that methyl group is. The methyl group's going to go in the back to where that hydroxide is, and then the hydroxide is going to spin around and move to where that bromine is. So that's an option. Or we can swap, and trace and do an arc. So I'll tell you about that. This process is okay. It sort of works, but it gets more complicated when you get into more complicated compounds. So I'm not going to focus on that one because it's not going to be helpful, especially when we have ringed structures. So the swap, trace method is the best way to deal with this. So let's walk through that. So the first step is to identify the priority. So this is the low priority 4. And we have 3, 2, and 1 based off of the atomic weight. What we know is that this group, because there's a dash here, this needs to be the low priority. So what we can do is we can swap these groups, but we don't actually have to swap anything. We can just swap the numbers. So we can take these numbers and move the numbers around. And that's going to, when we do the first swap, this actually gives us the enantiomer. So the opposite compound. Remember when we were back here, all we did, the difference between this R enantiomer and the S enantiomer, were that one of these groups switched spaces. So we can swap these and it will turn into the other enantiomer. And then if we switch 2 more, then it will switch back to the starting enantiomer. So if we do a swap, we're turning it into the same thing. We're just moving those groups into the position that we want them to be into. So let's do that. But instead of moving the hydroxide, methyl groups, or anything else, I'm just going to move the numbers. I'm going to keep track of where I move them to. I know that I need the low priority thing in the back. So what I'm going to do is I'm going to swap the 4 and the 2 so that the 4 is in the back and now the 2 is no longer in the back. So that's now my enantiomer. I want to do another swap to turn it back, get back to the original. So to get back to my original compound, I need to swap 2 other things. I'm going to swap the 3 and the 1 now. All right, so now I can trace. I did the swap, I did the second swap, and then I'm going to trace arc. So I go from 1 to 2 to 3. I ignore the 4th, the one in the back. So this is an S formation here. So this is the easiest and the best way and the most systematic way to do this, and I wouldn't recommend redrawing. That gets too complicated and it doesn't work for every situation. Here's another example of just showing you that what this swap and swapping does. And again, we can just show you, I can show you this by showing you the priority groups where we would find them. We'd have the low priority is the methyl group. So methyl group, these are the same 4 different things on all 3 of these different groups. So methyl group and the methyl group and the methyl group. So I've labeled them 4 in each position. Hydroxide's a 2 in each position, and the bromine is a 1 in each position. Ethyl group is a 3 in each position. So I'm swapping the 4 and the 2. So I have a 4 and a 2. I'm swapping the methyl and the hydroxide. So this is the same. And the 1 and the 3 are in the same position after the first swap. So then next, what we can do is we can also move through the second swap where I'm switching the bromine and the methyl groups. I'm swapping those out. So you can see it doesn't really matter if I move the elements that are attached to that chiral center or if I just move the numbers. It's the same thing. I still have the same priority groups, and really this is the enantiomer in the middle, and then I go back to the original compound in the end. So we can just swap the numbers. We don't have to redraw everything out. So it can be just like this. It doesn't really matter. We don't need to know really what's on the outside as long as we know what the priorities are and how they're organized. So here's an example of where redrawing is going to be really difficult. It's going to be hard to redraw this, right? To think about moving this and shifting this in 3-dimensional space. But if we know this is a chiral center here, I can determine the mass of things. So I can go down here. This is a methyl group, or a carbon, a chlorine, and an oxygen. So the carbon group, this is going to be the low priority. This is going to be 4 down here. Then the next is going to be the carbon attached to the oxygen. That's 3. Then we have an oxygen that's going to be number 2, and the chlorine is going to be number 1. So that's the priority organization. Now, number 1 priority is in the back, right? We have this dashed line. That means that chlorine's in the back. We need the low priority in the back. So we need to swap this out and move these around. I'm going to switch 4 and 1 so that 4 is in the back and 1 is not in the back. And then, so that's the enantiomer right now. We need to swap again to get back to our original compound. So now I have this new group. I have a 1, 2, 3. I'm going to trace from 1 to 2 to 3. I'm going to ignore 4. And this is an R enantiomer. Okay, so we're going to practice this in class so you can take your, try to identify the priority and then number those, and then do, if the low priority is not in the back, do that swap, and then trace and determine if these are R versus S enantiomers. And again, we'll continue this in the class and discuss these and go over the answers for these as well.